Throughout history, humanity has gazed at the stars and wondered, are we alone? This question has sparked the imagination of countless generations, inspiring myths, legends, and scientific inquiry. From the ancient astronomers who charted the movements of celestial bodies to the modern scientists who probe the depths of the universe, our fascination with the cosmos has been a constant thread in the tapestry of human history. What mysteries lie hidden in the vastness of space? The universe is a boundless expanse, filled with wonders that challenge our understanding and expand our horizons. Each new discovery, from distant galaxies to exoplanets orbiting far-off stars, brings us closer to answering fundamental questions about our place in the cosmos. The dream of interstellar travel, once relegated to science fiction, is now a frontier of scientific exploration. Visionaries like Jules Verne and H.G. Wells imagined journeys to other worlds long before the technology existed to make them possible. Today we are turning those dreams into reality, with spacecraft designed to traverse the vast distances between stars. The desire to reach out to other star systems is deeply ingrained in our nature. It speaks to our innate curiosity and our relentless drive to explore the unknown. From the earliest explorers who sailed across uncharted seas to the astronauts who ventured into the void of space, the spirit of exploration has always been a defining characteristic of humanity. It's a testament to our curiosity and our drive to explore the unknown. Every rocket launch, every mission to space is a step forward in our quest to understand the universe. These endeavors inspire future generations to look up at the stars and dream of what lies beyond. For centuries we were limited by technology. Our ancestors could only observe the stars with the naked eye or through rudimentary telescopes. Despite these limitations, they made remarkable discoveries, laying the groundwork for the advanced astronomy and space exploration we have today. We could only observe the stars from afar. The vast distances and harsh conditions of space seemed insurmountable. Yet, with each passing century, our tools and techniques improved, allowing us to peer deeper into the cosmos and uncover its secrets. Today, we stand at the cusp of a new era. Advances in technology have brought us closer than ever to achieving interstellar travel. From powerful telescopes that can detect planets in distant star systems, to spacecraft capable of traveling at unprecedented speeds, we are making strides that once seemed impossible. We are developing technologies that could make interstellar travel a reality. Innovations in propulsion, energy, and materials science are paving the way for missions that could take us beyond our solar system. These breakthroughs are the result of decades of research and collaboration among scientists, engineers, and visionaries. Our generation could be the one to take the first steps towards other stars. The young minds of today, inspired by the achievements of the past and the possibilities of the future, are poised to lead us into a new era of exploration. Their passion and ingenuity will drive the innovations needed to overcome the challenges of interstellar travel. This is a defining moment in human history. The decisions we make and the actions we take now will shape the future of space exploration for generations to come. As we stand on the brink of this new frontier, we must remember the lessons of the past and the potential of the future. The challenges ahead are immense, but they are not insurmountable. With determination, creativity, and collaboration, we can overcome the obstacles that stand in our way. The journey to the stars will require the best of our abilities and the full extent of our ingenuity. Just as we have overcome countless obstacles in the past, we can find solutions to the problems of interstellar travel. History is filled with examples of human ingenuity triumphing over adversity. From the Wright brothers' first flight to the Apollo moon landings, we have shown that no challenge is too great when we work together. The journey will require global cooperation, groundbreaking innovation, and an unwavering belief in the human spirit of exploration. Nations must come together, sharing knowledge and resources to achieve the common goal of reaching the stars. This collaborative effort will not only advance our scientific understanding but also foster a sense of unity and shared purpose. But the rewards, both scientific and philosophical, will be immeasurable. The knowledge we gain from exploring other star systems will deepen our understanding of the universe and our place within it. The philosophical implications of discovering life beyond Earth, or understanding the origins of the cosmos, will resonate for generations. We are on the verge of an incredible adventure. The journey to the stars is not just a scientific endeavor, it is a testament to the enduring human spirit. As we reach for the stars, we are reminded of our boundless potential and our unyielding desire to explore the unknown. The future of interstellar travel is bright, and the possibilities are endless. To comprehend the challenges of interstellar travel, we must first grasp the vastness of the universe. The universe is an expansive, almost unfathomable space, filled with countless stars, planets, and galaxies. Each of these celestial bodies is separated by immense distances that are difficult for the human mind to truly comprehend. Distances between stars are not measured in kilometers or miles, but in light years. A light year is a unit of astronomical distance that represents the distance that light travels in 1 year. This measurement is essential because the numbers involved are so large that conventional units like kilometers or miles become impractical. 1 light year is the distance light travels in a year, a staggering 5.88 trillion miles. To put this into perspective, light travels at a speed of about 186,282 miles per second. In just 1 second, light can travel around the Earth 7.5 times. Now, imagine this speed sustained over an entire year. Proxima Centauri, our closest stellar neighbor, is over 4 light years away. This means that even the nearest star to our solar system is still an incredibly vast distance from us. If we were to travel to Proxima Centauri using current technology, it would take an unimaginable amount of time. Consider that the Voyager 1 spacecraft, the farthest human-made object from Earth, travels at a speed of about 38,000 miles per hour. Launched in 1977, Voyager 1 has been traveling through space for over 4 decades, yet it has only just recently entered interstellar space. At this speed, it would take Voyager 1 over 70,000 years to reach Proxima Centauri. This highlights the limitations of our current propulsion technology and the need for significant advancements if we ever hope to explore beyond our solar system. This incredible distance underscores the need for revolutionary propulsion systems. Concepts such as warp drives, ion propulsion, and even antimatter engines are being explored as potential solutions to the problem of interstellar travel. Even at the speed of light, a round trip to Proxima Centauri would take over 8 years. This is because light, despite being the fastest thing in the universe, still takes time to travel across the vast distances of space. This means any communication with a spacecraft at Proxima Centauri would be delayed by years. For instance, a message sent from Earth would take over 4 years to reach the spacecraft, and another 4 years for the reply to return. Such a delay would make real-time communication impossible. This presents a significant challenge for mission planning and control, as immediate responses to unforeseen events would be unfeasible. It also highlights the need for highly autonomous spacecraft capable of making decisions independently. These spacecraft would need advanced artificial intelligence systems to navigate, conduct scientific experiments, and handle emergencies without direct human intervention. Traditional chemical rockets, while powerful, are ill-suited for interstellar travel. These rockets have been the backbone of space exploration since the mid-20th century, propelling humans to the moon and sending probes to the far reaches of our solar system. However, their reliance on chemical reactions to produce thrust presents significant limitations. They rely on burning fuel, which is heavy and inefficient for long journeys. The sheer amount of fuel required for extended missions makes it impractical for interstellar travel. The weight of the fuel itself becomes a major hurdle, as it requires even more fuel to propel the additional weight, creating a vicious cycle. To reach even a fraction of the speed of light, we need to look beyond chemical propulsion. The vast distances between stars mean that even the closest ones are light years away, making current propulsion methods inadequate for such journeys. We need innovative solutions that can overcome these immense distances. One promising avenue is ion propulsion. Unlike chemical rockets, ion thrusters use electricity to accelerate ions, creating thrust. This method is far more efficient, as it requires significantly less propellant and can operate for much longer durations. Ion thrusters use electricity to accelerate ions, creating thrust. The ions are expelled at high speeds, generating a continuous, albeit low, thrust. This continuous thrust can gradually accelerate a spacecraft to very high speeds over time, making it a viable option for long-duration missions. While the thrust is low, it can be sustained for long periods, allowing a spacecraft to reach high speeds gradually. This makes ion propulsion particularly suitable for missions that require sustained acceleration over months or even years, such as journeys to the outer planets or beyond. Another intriguing possibility is solar sails. These large reflective sails would harness the momentum of photons from the sun to propel a spacecraft. The concept is similar to how a sailboat uses wind to move across water, but instead, solar sails use light. These large, reflective sails would harness the momentum of photons from the sun to propel a spacecraft. As sunlight strikes the sail, it imparts a small amount of momentum, gradually accelerating the spacecraft. Over time, this method could achieve significant speeds without the need for onboard fuel. The Breakthrough Starshot initiative is exploring this technology, aiming to send a fleet of tiny spacecraft to Alpha Centauri within a generation. These small, lightweight probes would be equipped with solar sails and propelled by powerful ground-based lasers, potentially reaching speeds of up to 20% the speed of light. Perhaps the most ambitious concept is the Alcubierre drive. Named after physicist Miguel Alcubierre, this theoretical drive would manipulate space-time itself, creating a warp bubble around a spacecraft. The idea is to contract space in front of the spacecraft and expand it behind, effectively allowing the spacecraft to surf through space. This theoretical drive would manipulate space-time itself, creating a warp bubble around a spacecraft. By bending space-time, the spacecraft could travel faster than light without actually moving faster than light within its local frame of reference, thus avoiding the relativistic problems associated with near-light-speed travel. Theoretically, this would allow faster-than-light travel without violating the laws of physics. However, the energy requirements for such a drive are currently beyond our technological capabilities, and the concept remains purely speculative at this stage. However, the Alcubierre drive remains highly speculative. It presents numerous scientific and engineering challenges that we have yet to overcome. Theoretical models suggest it would require vast amounts of energy, possibly more than what is available in the entire universe. It would require exotic forms of matter with negative mass energy density, something physicists have yet to discover. This exotic matter is purely hypothetical and has not been observed in nature, making the practical implementation of the Alcubierre drive a distant dream for now. Section 4. The Energy Challenge. Even with these advanced propulsion systems, the energy requirements for interstellar travel are astronomical. Consider that the energy needed to accelerate a spacecraft to a significant fraction of the speed of light is many orders of magnitude greater than the energy consumption of our entire planet. Harnessing such power would require significant breakthroughs in energy production and storage. Fusion power, the energy source of the stars, holds promise. By fusing light atoms like hydrogen into helium, we can release immense amounts of energy. However, achieving sustained fusion reactions remains a major scientific and engineering challenge. Another possibility is antimatter, which, when it comes into contact with matter, annihilates and releases pure energy. However, producing and storing antimatter is even more challenging than fusion. Section 5. The Perils of Deep Space. The interstellar medium, the space between stars, is not a perfect vacuum. It is a harsh and unforgiving environment. It's teeming with high-energy cosmic rays, interstellar dust, and extreme temperatures. Exposure to cosmic radiation poses a significant threat to human health. Long-duration space travel would require developing effective radiation shielding, a challenge that scientists are actively researching. Interstellar dust, though minuscule, can pose a threat to spacecraft at high speeds. Even microscopic particles can cause significant damage upon impact. Designing spacecraft with robust shielding and self-repair mechanisms will be crucial for interstellar voyages.